Hello, my name is also John with my colleague Chiparo Derek, and our machine learning project it's entitled in contrastive distillation for seed variety classification with capsule network and mechanism attention. And our project is entitled Smart Harvest. So on our first slide, according to UN, one of the major causes of hunger is failure by farmers and researchers to access timely and accurate agriculture information. So this gap has led to poor seed selection, low crop yields, and food insecurity, especially in developing countries where farming is a backbone. It's on record that very many farmers misclassify seed varieties, and this is resulting into poor crop yields, hence affecting the economy negatively. So the traditional methods that are being used for seed identification, they are often manual, they are slow, and they are prone to human errors. So it's making it hard for farmers to make informed decisions. So there is a big importance to address this problem so that we can ensure food security, sustainable agricultural growth, and hence at a later stage it can boost the economy. So as you can see here, we have two types of genetics, and with our naked eyes it becomes difficult to tell the difference. So our project it's mainly focusing at developing an AI-driven seed classification system that's going to help farmers to make informed decisions. And our key objectives are accurate classification, efficiency and scalability, user-friendly system, and to also develop and also support agriculture innovation. So about solution overview, our project it's aiming at developing machine learning and deep learning model to classify seed varieties more accurately, and we are using deep learning techniques such as contrastive knowledge, capsule network, and attention mechanism in order to enhance our model performance. And our innovation aspects are high accuracy, robust model, scalable and efficient model that is applicable in the real world. So about the data we used a private data set from a private science researcher, and it was a Guinness image data set that contains about 592 image seeds that we are categorized in 5 groups, and those are S2T, S3R, S4T, S7T, and S9T. And after getting this data set, we did data processing and pre-processing on it. And then after in pre-processing, we used techniques such as normalization, resizing, data augmentation. And after this, we went and we developed a model. And we developed a number of models, and we developed models that were aligned in our primary goal of accuracy, efficiency in agriculture seed classification. And after this, we did model evaluation where the distilled mobile net model came out to be outstanding with accuracy of 98.3%, and this is the model that we went ahead to deploy. So about the system architecture, we went through the process of collecting data. Then after collecting this data, we went ahead and we did augmentation. Then we developed a model. Then after we trained the model, and at the later stage we deployed it. I think in implementation details, we used Python as our language, and we had libraries such as TensorFlow, Keras, OpenCV, Flask, and the platforms that we used are Cargo, Flask, and our local server for deployment. I think that's all. Let me call in my colleague to take you through the next slides.
My name is Derek. So on the next slide, I have results and evaluation. So these are the results of our model that we deployed, and it was able to obtain an overall accuracy of 98.33%, precision of 0.9846, recall of 0.9833, and F1 score of 0.833. Then with the confusion matrix that we obtained, this confusion matrix was obtained after using a test data set of 60 images with each class given 12 image samples, and our model was able to classify the varieties of classes S3R, S2T, S9T, and 7T. And then with S4T, it correctly classified 11 image samples and misclassified only one image sample as of S4T as S9T. Then on the next slide, I have the impact and relevance. So with relevance, we are reducing dependencies on traditional variety classification methods, food security and crop selection, and then seed production and marketing. So our project aligns with SDGs, like the zero hunger, responsible production and consumption, and then industrial innovation. Then we are targeting users like farmers, agricultural researchers, and then the big seed companies. On the next slide, I have intellectual property and innovation. Of course, our project needs to be protected because we are using new algorithms, we are using unique processing techniques, we are automating the system, which and this automation and this automated system, I believe it's a new thing on the market. And then with protectability and patentability, our project is patentable, cooperatable, and we will also have trade secrets like hyperparameter tuning strategies and data augmentation techniques that we used. And then on the next slide, I have monetization and scaling. With monetization, we are looking at commercialization strategies because our project basically is a software as a service, which will be deployed on a cloud-based, which will be used as a cloud-based risk classification. It's a mobile app. We have a strategy like mobile application platform where singularity classification can be carried out on the go, basis. Then with market potential, we are targeting sectors like farmers and then Uganda at large. So with SWOT analysis, we have strengths like high accuracy. Our model is highly accurate, and the weakness is in the data set preparation. Our model is also scalable, but again we have weaknesses like barriers in rural areas where internet connection can be poor. And then we have with the opportunity rising that there is a growing demand for precision agriculture, and there are government and NGO funding. However, there are threats like competing AI singularity classification solutions and possible resistance to AI by the government. And then this is how our model performs. As you can see, the user can select a given seed variety and then upload seed to our system, and the system will predict the class, the variety of the seed uploaded, as you can see in the image in the video. Then on the next slide is the time contribution is, and this is what each member contributed towards the project development. And then with lessons learned and challenges, of course we faced some challenges like the data set limitations, hardware constraints, for example RAM and GPU, the model generalization, and then deployment limitations. And then with lessons, we are able to learn AI-based classifications, the contrastive noise distillation in enhancing performance of a given model, the dataset processing techniques, and model deployment. Then with future works, we intend to enhance model performance, better deployment optimization, and then user experience and accessibility, and then monitoring our model. With future scaling and extension is we intend to expand to other properties for a broader agriculture impact, and then combine image data with textual descriptions to enhance classification. And then on the next slide we have the conclusions. So in conclusion, our model so far have achieved successful so far we have developed successful an AI-driven ground-net variety classification. We have achieved the high accuracy of the model, and then we have deployed a user-friendly Flask-based web hub for real-world application as I showed you in the video. Then with value and impact, we are helping farmers and agriculture stakeholders to differentiate seed varieties, and we are enhancing efficiency, reducing misclassifications, and supporting informed decision making. So in conclusion, our solution bridges the gap between AI and agriculture, and we are offering a practical, a scalable tool for improving crop classification and decision making. And the future of smart farming starts with us within our project. So that is what I had for you.